Okay, yeah, so you should have noticed in the lecture notes, it'll say just reference C slides from lecture 4 because we weren't quite done with that yet. But what we ended on when we were just introducing consolidation is what an actual measurement from a real lab report looks like. And we see even though we conceptualize it as two vertical lines, we have to remember that the actual raw data is not producing a straight vertical line. So there's always assumptions and always a lot of room for error when we're talking about the consolidation test. And what that means, sorry, I'm gonna have to start standing closer to this because I think the audio doesn't pick up very well. But what that means when you're working on predicting the actual field settlement or the consolidation of real soils is we cannot be super accurate. So when you start working as a geotechnical engineer or start working with geotechnical engineers, providing the anticipated settlement of a project site to 4 millimeters or 0.4 of a millimeter, that's just, there's no way we can be that accurate because we're making all these assumptions with our raw data. So I'll show an example here that talks about that. But remember this CC right here, that is just the slope of this curve right here. So the tangent to this point, and that's to the pre-consolidation pressure. And then the CS should theoretically be the same slope as these two. You can see just looking at it visually, it doesn't look like they're the same slope, right? So again, there could be two values of CS based off of the stress level or the unloading level that you have. And so to find this CC value, it's not just a simple slope equation because this applied pressure, again, is in a log. So it's a semi-log plot. So always keep that in mind. We have to include the log in there when we're talking about measuring the slope. It's not just the rise over run. But what it is that E1, E2, and then divided by log of the sigma 2 minus log of the sigma 1. So what you would do is if you had this line, then you would just find 2 points. Erase this red so it's not just a bunch of red everywhere. So just find 2 points. Let's say right here, this would be our sigma 2, and then just find another point that's easy to read. What was one that I used? 7. Yeah, right here. So these would have the corresponding sigma 2 and sigma 1, and then E1, and then corresponding sigma 2 and E2. So just like you would do your X and your Y, you find 2. And if you have a report like this, again, we have to read this in log form. So keep that in mind when you're looking at the axes. Follow it down. Most real engineering reports will provide the trend line, or not the trend line, the grid lines like this. Again, know what you're reading. This is the log on the x-axis. So in this example, let's say our E1 is 1.27 on the y-axis, and the corresponding sigma 1 for that would be somewhere here. So this unit is in TSF, so tons per square foot. So that's 5.5 TSF. For the second one, our E2, right here, we'd read this over somewhere here. So that's just 1.8 or 1.08 void ratio. And then our sigma 2 is going to be 10, 20, 16 TSF. And then we would just plug it in here. Go back to red real quick. And again, the values are switched on the bottom, so we get a positive slope. Because if you were to do this normally rise over run, right, that would be a negative slope here. So for this, we see that CC is equal to 0.41. So has anyone that like seen these reports? Like I know some of you guys work and some of you guys are already in like a geotechnical role. Like have any of you guys seen this report and used this technique to find the CC value? Anybody? Okay. Well, what you'll see when you come across this, a lot of times, like the effort to retrieve a soil sample like this and run these tests aren't worth the time and money, because again, this test takes over a day, like at least a couple of days, because you do 24 hours in between each incremental loading. So what we said before was there was all these different correlations to find that CC value. Because what we'll see today is that CC value is really important in predicting the actual settlement of the field conditions and of the loading conditions. So what else we see from this, some words on the bottom that will probably look familiar. We see these moisture contents down here. So the natural moisture content, it was determined that the moisture content of the soil was 50%. Other things like the Atterberg limits, if you remember here, the liquid limit, plasticity index. We have the pre-consolidation pressure of 4.75. And then we have the current overburden pressure of 1.38. So what does that mean of this soil? What type of soil is this? Over consolidated. Yep, because our current is less than the past. Then we have the void ratio and stuff too, and it shows that this is a gray fat clay. So you will probably see a report like this that's produced. And again, thinking back to what the Atterberg limit test was from geotech, like the little cup that goes back and forth. Like there's just a lot of area for mistakes and a lot of area for error in these. So take these tests for what they are, not like, end all be all stuff. Well, okay, so we got a CC value of about 0.41. Just for fun, let's go and some of those original correlations that we talked about. Let's just compare those and see how these correlations would work up against it. So the actual, we're just going to call that test the actual here, right? And then the ones from like the 1940, this guy, the Skempton relationship, this was, you said what, 0.009 times the liquid limit, which is down here, so 98, so liquid limit minus 10. So that equals to 0.009 times 98 minus 10. And that equals about 0.792. So 0.792 compared to 0.42. And this is a common correlation that is used, and some people may just use blindly, right? But we can see right off the bat, these values are really different. Some of the other ones, the Rothenwood one from 1978, this one is 0.5 times the specific gravity, so 2.7, which is determined here, or divided by the PI, which is the plasticity index, which is 79 divided by 100 because it's in percentage form. We see for this one, we get an CC value of 1.070. So compared to the actual data of 0.42. So you can kind of see the trend here. This one too, the Rendon-Herrero. And again, if you go back into your notes from lecture 4, you'll see the actual equation here. I'm not going to include all of it, like all the variables. But all these correlations, even like some of these crazy, like fancy looking equations like this, that should be more accurate because they look harder and fancier. So that must mean they're more accurate. We still get results that are pretty far off. This one too, the Alcafia and Anderslin, they produce 4.8. So if you remember, if you go back to the other when we started talking about these, some of these soils are meant for specific types of soil. So if you remember this one and this one, that was for NC clay only. So be really careful when you start working. If you're in a geotech firm or if you're working with a geotech and somebody says, hey, like we need to estimate the CC value or we need to estimate the consolidation, like just find some correlations and plug it in and use that value. Like we have to make sure we're using the correct correlation for the type of soil that we're working with. Because again, here we have our current, our sigma prime is equal to 1.38. And then from here, our pre-consolidation pressure is 4.75. So that, therefore, this is an OC soil, over consolidated soil. So that's what I was talking about last week. And that's why you'll start seeing, hopefully, this being more utilized more in the future, where specific geologic formations in specific areas of like a state or region have their own correlations. So something like this from the FDOT. And they require a lot more input and they're not pretty equations, but they're much more accurate because they're designed for the actual soil at the site and not the entire soil from throughout the entire, the US. So again, keep this in mind if you come across this when you start working, because yeah, again, no matter, even if you don't work in geotech, you're going to work with geotechs and you'll probably eventually see some consolidation reports or something. Just know where that information comes from. All right, so just in summary from what we were saying last week, the clays have the long-term settlement, and this occurs as the pore water pressure dissipates after loading. So we only see this in low permeable material. So consolidation in clays or consolidation in sands, consolidation in gravels, that doesn't exist. There's no long-term settlement. All the settlement occurs right when you load it. So only in clay and some silts do we have this issue. Behavior is important, just like the stress strain diagram. So we also want to find the CS. This is also or CS here. So these are called the same thing, recovery or the swelling index. And then we also have another important aspect is the over-consolidation ratio. That over-consolidation ratio is the pre-consolidation pressure divided by the current effective stress. So that pre-consolidation pressure is the past max divided by the current. Hopefully by now, finding the current effective stress, everyone's familiar with by now, by going through the in situ stresses and everything. So then there's two cases that we have. We have a normally consolidated This is shown generally by just N.C. And this basically means that the current stress that it is feeling is the max stress. So what that means is your current stress is equal to the past max stress, which means the OCR is equal to 1. So we can never have an OCR less than 1 because current and past would always be equal to each other. That's the bottom, that's the lower boundary. The other option is the over-consolidated. And again, try not to let that term over get too confusing. The over just means that it has once, like historically, felt a higher stress. So again, I'm using the word felt. Again, I used like the illustration that helped me remember this. Like in terms of like salaries, like generally the more you work or the more like effort that you put towards your job, generally the more you should get paid, right? So if you have used to work a lot and have a certain salary and then cut your hours in half, and now you're carrying less workload, but you still get paid the same amount, then you're overcompensated. So you're getting paid more than you're worth. So same with this, the clay, if it once carried a higher load than what it is carrying now, then it is over consolidated. So overcompensated, over consolidated, or even like overqualified. You could think of it that way. Like if you're working on a lower end job and you once were like a CEO of a company, you're probably overqualified for that current job. That kind of thing. Okay, so that was from before. Now what we're going to be looking at is the consolidation, especially field consolidation. So we'll start getting into why we do these tests in the lab and what they actually tell us about the soil at the site when we're loading. So again, you guys, this is already stuff you should see in this, the slides 15 through 18 from lecture 4. This is all new stuff. Same chapter here for this one textbook, but now they switch it here to chapter 9, consolidation settlement of shallow foundations. I'm really just going to be kind of introducing the theory today for it. So we'll talk about the estimation of consolidation settlement in the field, and of course, focusing on normally consolidated soils, but you'll see there's different equations and different like methods that we'll use for over-consolidated soil in different cases. But that's why thinking of it as like the roadmap of which path it's taking deformation-wise would be the easiest thing, like mentally for you to think about. So we'll cover that here in a second. Just wanted to recap a few things from the quiz too. Again, don't sweat it too much if you're like not doing too hot on these quizzes. There's going to be a lot of like quizzes throughout the semester, so it'll even out. You have plenty of time to make up ground. These quizzes are important for me because it kind of sees where everybody's at, just course-wise, and making sure that some of the key fundamentals are all being understood. But if you guys, well, I guess, yeah, a lot of you guys didn't have me for a few semesters ago now. But these quizzes are also going to be kind of indicative of what the information on the quiz, on the test is going to be. So if there's any concepts on these quizzes that aren't making sense, then try to dig into that a little bit more, ask me about it. And, because there's a good chance you'll see this information again. But wanted to just recap a few things. We talked about liquefaction. So liquefaction only occurs in a permeable soil. So it must be most of the time it's going to be like a clean sand that this forms in. So you won't see it in organic soil. You won't see it in like any low like permeability silt or even clay. Like you'll never see liquefaction in clay. It's all going to be sandy areas. And like again, if you remember some of the slides that we were showing liquefaction, there's always water involved, and they tend to happen near like beach sediments and stuff. So like in New Zealand, a lot of it happens. In California, it can happen. And if you think about like, if you've been to California, you could probably imagine it's just a lot of sand, like, because it's right on the coast. New Zealand too, it's an island, so there's a lot of sand on the coast. So think about that, like, physically where you see these examples of liquefaction occurring. The other one that's going to be important to know for this is again, that 2-to-1 method to determine the increase in stress. So even though the equation looks kind of weird because there's a bunch of things here, all you need to know, or it's easier to remember what this is actually showing. So this is showing, technically, this is showing the load at the surface. So load as in like the actual force or the pounds or kip or newtons or some type of load, not a stress. and it's dividing it by a hypothetical area at the depth in question. So that area is increasing on a slope of 2 to 1 as we go further down in depth. So in this case, it's a hard, like weird little funky looking 3D thing. About that area, if an area has B times L at the surface, then that area at the bottom or at whatever depth is just going to be B plus the Z depth times L plus the Z depth. So again, this is really just area P divided by A. But that area again is at the depth. So we follow that 2 to 1 slope. That's what's physically happening. We're assuming that it's dissipating. So with depth, since this P is not changing, the area is getting larger with depths. We should see that delta sigma decrease the deeper we go, right? Because it's being distributed by a wider footprint. Just keep that in mind, because again, like this equation is good if you're using rectangles, but if you have a circle or any other weird geometry, then you may need to, you can't use this one because this is only for rectangles. And that was a question I saw like on the PE. So it wouldn't surprise me if you see this on the FE or if you see it like in the future on the PE or something. Okay, so the consolidation, when we talk about consolidation as a whole in clays, what we're actually talking about are 3 stages. Now, the majority of the loss of volume or the majority of the settlement occurs from our primary consolidation stage. So again, if we could see this y-axis is representing the deformation. What this is actually telling us is this is the deformation from stage 1. This is the deformation from stage 2. This is the deformation from stage 3. So in respect to the other 2 stages, our primary consolidation is generally the one that produces the most deformation. So 9 times out of 10, if you're on a project, you're going to be just focusing on the primary consolidation. But some projects or some cases, you still can have a considerable amount of secondary consolidation. And a big one we talked about last week, this happens in organic soils. Because what we're actually having physically in this secondary consolidation is the readjustment of the soil fabric. So the actual fabric itself breaks down. And mineral soils, like your typical clay and sand and silts and stuff, that rock, that little tiny miniature rock, isn't really going to break down that much. But in organic soils, you could easily, compress a leaf, or sticks, like decomposing sticks. So secondary consolidation occurs a lot. So again, water, this is the water leaving here, and then this is the actual structure crushing here. But again, as I said, most of the time you're going to be focusing on the primary consolidation. So today we're just going to be deriving and showing how we get from a consolidation test to the actual field prediction of a project and how much the ground is going to settle during this. So you should have like these little like up in the top right corners. I get that there's a bunch of things here and it's, you only have a finite space. So just keep that in mind. Like you can note this if you don't already, so you can keep your notes together a little bit easier. So again, what we're showing when we're actually doing this consolidation test, this is a 1D version of consolidation. So if we actually have a little magical box of soil here, we are loading it in one direction. So we'll just say this is a P. And everything else is going to be confined. That means it can only change shape in one direction. We can only show a deformation in one direction here. So this is what it's going to look like after loading. If it has an original height H, I always forget about that one. Then what we're going to say is it changes due to this loading as a delta H. Again, the one way we can visualize this in 1D, but just for the sake of like pressure and everything, what we could say is this is technically just a unit volume. So let's just say that this area, there's actually an area that it's being applied to, right? But it has a depth of 1, so 1 unit. That's how we go from like 1D to like a 2D standpoint. So this change of volume, what we'll see and what we've seen from the consolidation test, is represented by void ratio, right? So a change of void ratio. Because what we're doing in primary consolidation is we are just losing the water pressure, but our volume of solid is staying the same. Remember, secondary consolidation, the volume of solid actually crushes. So this is not secondary consolidation. This is primary consolidation. So we're assuming that volume of solid is staying the same. So if the void ratio is the volume of voids divided by the volume of solid, any change of void ratio is just going to be represented by the change of the volume of voids. Do you see where that's coming from? So change of void ratio, we'll always accidentally do sigma, I'm sorry. Change of void ratio is really just this, because our volume of solid is not changing, it's staying the same in the primary consolidation. So since we are in 1D / this 2D space, the change of volume is only going in one direction, but we can still show this, that change of volume is technically from a change of height times an area, and the volume of solid is just that original height times an area, but that area is staying the same. Right, this is the area here technically. That area is staying the same because it's only going in one direction. So the area here is same area here. So of course we can cancel that out. We see the void ratio, change of void ratio is change in height over the original height. So again, the void ratio, just repeating this, E is equal to the volume of voids divided by the volume of solids. So we can rewrite this as the volume of voids is equal to the void ratio times the volume of solid. Again, that would mean that the change of voids, change of volume of voids, is equal to the change of void ratio times the volume of solid. So instead of the change here, what I'm going to represent as same as before, we just had a subscript 1 and a subscript 2, right? Or a subscript 0 for the first stage and then subscript 1 as the second one. So this is just going to be the same as saying the volume of voids, what I'm going to say is 1 is equal to the void ratio 1 times the volume of solid. So if we were to draw the free body or the phase diagram from before and everything, we know that the total volume is consistent of a volume of voids and then a volume of solid. That's our volume of voids and our volume of solid. If we think about what we're doing during the primary consolidation, we're just lowering the volume of voids. But our volume of solid is staying the same. But compared to the first step, so this is, I'll just say this is step 0. This is step 1. This is 1. We have this change of voids. So whenever we change the voids, we're also changing the new total voids, right? So now we also have this volume total in step 1. So we're step 0 to step 1. That's why the subscript 1 is there. So our total voids. Just total voids is equal to the volume of voids plus, the total, plus the volume of solid. So therefore, our total voids from this equation from our void ratio, our total voids also equal to the volume of, we do E times the volume of solid plus the volume of solid. And this is equal to Vs times 1 plus E, right? All we're doing is factoring out the Vs. So we'll have E plus 1 times quantity of Vs. And that's for the first time step. So we could do this for the second time step, and it'd be the same equation. But what we see is our Vs stays the same because, again, we're not changing our Vs. All we're doing is changing the void ratio. That's for the first time step. We could do this for any time step. So if we did V2, then our Vs would still remain the same. Again, I know, like, for me, it was always confusing seeing all these little subscripts and zeros and ones and stuff. But what this is just representing the times that we're loading the soil and the measurements in between. So all the deltas that we see, the delta V's, are occurring in between these two time steps. So it'd just be the subtraction between these two, right? Delta V1, this would be delta V2. So the settlement is what we want to find, and the settlement is actually in the field condition, like that, not in the lab, but the field. What we see is that this is represented by the change of volume and then normalized by that original volume. That delta V, using the same subscript as before, that's the original volume minus the volume at step 1 divided by the original total volume. So from the previous page, we had all these versions of it, the volume of solid and the void ratio. Now what we can do is plug those in for this equation. So we have the volume of solid plus 1 plus E, the original E, minus the volume of solid, 1 plus E subscript 1, divided by Vs 1 plus E. So again, these equations were from the previous slide. These are from the different time steps. So previous slide. As I said before, primary consolidation the Vs doesn't change. So since our Vs doesn't change and we have Vs, Vs, and Vs in the equation for our settlement, then of course we can just cancel all of those out. So what we see then is our change in volume normalized by our original volume is equal to, if we were to factor all these out, this equation out, I can just do it actually real quick. What we'd see is 1 plus E minus 1 minus E1, right? Because what we're doing is factoring or changing these guys out. Taking these guys out and factoring that. All divided by 1 plus E. So the ones cancel out. And what we're left is E minus E1. So the original void ratio minus the new void ratio, now that it's been compressed, that's divided by 1 plus E. Again, when I said void ratio is important because we freaking use it for everything when it comes down to this. Now, again, this delta, this E minus E1, that's the original void ratio minus the new void ratio that it's been compressed. So that again is the delta. So what we show this as is delta E, so the change in void ratio divided by 1 plus the original void ratio. So again, since we are assuming 1D, we're in one dimension here. This is from before. Our delta volume is equal to really just the change in height. All right, I had some technical difficulties. We're back. What I ended on, which won't be an ending for you guys, but since we are assuming one dimension here, that means volume. Instead of volume, we can just look at it as an equivalent height. And since we had this equation from previously, then that change in height divided by the original height is equal to 1 plus, or the change in void ratio divided by 1 plus that void ratio. Or what we will do is simplify this and solve for that change in height and put that h over on this side. And we're going to see this is going to be an important equation when we go from the lab to the field conditions. So specifically for NC clays, normally consolidated clays, and again, that is when our current effective stress is equal to the past maximum. What we know about normally consolidated clays are they follow, we're looking at the E log sigma prime plot here. What that means is that the current stress is at the maximum pass pressure, right? We just said that. So it would just follow a straight line as we add any change in stress. And that straight line follows the slope of CC, right? The compression index. That means the consolidation is dependent on any change of sigma as well as a change of void ratio. So again, what we found last time, don't know why I wrote in cursive right there, in general, the delta H is equal to H delta E divided by 1 plus E. This delta H, you can probably imagine that this could be beneficial because this delta H, this change in height, is this change of height of the sample. But if we extrapolate this to a full scale condition, where we have like site here with some clay layer here. This is a profile, right? So this is like a tree, whatever. We have some clay layer here. If we add a load on the surface, some structural load Q, then we know that this will be distributed through the subsurface using one of those techniques. And that would produce a delta sigma Z on top of this clay. And we could probably expect, just like the soil sample, to respond in the lab, that this would also respond by a delta H. So this clay sample obviously is going to have a void ratio. It's going to have a consolidation parameters. And we can find the effective stress at the middle and also use that. So from the consolidation test, we know that parameter, that CC, the compression index, is the slope. So that is E naught minus E1 divided by log of sigma 1 minus log of sigma naught. And again, these are backwards here just because the slope is not negative. One of the properties of log is we can rearrange this to make it look a little bit nicer. So if they're logs subtracting each other, then what we can also show it is this way by division. From our general consolidation theory, we have this one. Delta H is equal to H times the change of void ratio plus 1 plus the original. Now what we show, instead of small delta H, we generally show this as large uppercase delta H when we start going from consolidation theory to field conditions. So this delta H, if we visualize it in a one dimension, then this is going to be our settlement due to primary consolidation. So this is also commonly shown as SP for primary consolidation, or some textbooks show it as SC for just settlement due to consolidation. I'm going to try to always show it as PSP because we will be talking about secondary consolidation as well. So total consolidation usually includes secondary and as well as primary consolidation. So what we can do is plug these two equations in. Sorry to keep going back. You can see we have a equation if we solve for E, and we have a delta E here. So what we can formulate is equation for field conditions. So SP is equal to H times the change of void ratio divided by 1 plus the original void ratio. And again, that delta E is equal to something that is equal to CC times the log here. So we can find everything in this for the most part, right? H is a property of the site subsurface conditions. Our E prime, or sorry, our initial void ratio is based on the lab testing. We found this from our consolidation. We know our effective in situ stress from calculating if we know the densities of the soil and where the groundwater table is. And we can also find the next step of stress. So again, next step here this in the real world we know is really just our initial stress plus a change of stress, delta stress, right? So this delta should look familiar. This is just our delta sigma from loading at the surface. And this is what we went over last week and also in Geotech 1. So that's why that delta sigma Z is important. That change in vertical effective stress is important because now if we have that as well, then we can find our next step stress and feed that into our primary consolidation equation. So this is the equation that is obviously a little bit neater looking and not in my crappy handwriting. And again, this is only for normally consolidated clays. This is only if our current effective stress is equal to our past max pressure. Of course, though, if this was your past max pressure, then it should just be your current max pressure. So there's a few notes that are important to remember for this equation, besides it being just only for normally consolidated clays. So this delta sigma Z is produced from the structural loads. So this could be like an embankment or a foundation or a wall or anything that we've really covered so far from the beginning of the semester. This could be produced from the structural loads onto the clay layer. What we assume is it's acting on top of the clay layer. So we know delta sigma Z will diminish in value with depth. So this is actually a conservative estimate, right? This is because if we take that maximum delta Z at the top of this ground surface, just draw a little picture. Right, we have loading here. That delta sigma Z here is going to be largest when it's on top of the clay layer. So that's why we always take that one here, and it's almost as a conservative value. The effective stress is the effective vertical stress. And this is due to overburden. Overburden soil. And this is taken in the middle. taken in the middle of the clay layer. So unlike the vertical change of stress, we will always take our vertical effective in situ stress at H divided by 2 in the middle of the clay layer. Third thing, if the clay layer is large, and generally what large is, we're just going to say is greater than 20 feet in thickness, then you need to subdivide. And generally, when you see a clay layer that large, you would subdivide it anyways, because remember, you're taking just a very small sample out of this. So if we have a significant layer, then we want to, you take separate samples, do separate consolidation tests at different depths, and then be able to just split up that clay layer, and then your total primary settlement would just be all of the layers. Something like that. Okay, so let's go, let's look at an example. The soil profile is shown below. Estimate the primary consolidation settlement. Again, that's RSP of the clay directly under the point load. And then we're given the point load as a load of 1,000 kilonewtons. We're assuming the clay is normally consolidated, obviously, because we haven't gotten into over-consolidated yet. So what we're doing is we're finding the point right here in the middle of this clay, and something to always be on the lookout for the FE and also the PE, and for this class, you're often going to get more information than you need. In this example here, like, we don't really care about this sand layer right here. You could be given like the E value of the sand up here, the relative density, all this stuff. You don't really need it. So just keep that in mind. Keep an eye out for what you need and only take that. So we only care about the clay only. And what we have for, just to recap our equation here, CC H1 plus E naught. And our log, again, this is because it is normally consolidated. If it wasn't normally consolidated, we cannot use this equation. Remember, what we need is the effective stress in the middle. We also need the increase in vertical stress on the top. So let's do the effective stress in the middle first. So this is what at Z is equal to 4 plus 1.5, 5.5 meters down. Recall that the vertical effective stress is equal to the total stress minus the pore water pressure. So for the total stress, we know that this is just the sum of all of the densities and heights above our point of interest. So we have our density from our sand layer times the height of that sand layer, so 4 meters. And then we are taking it in the center here. We only have 1.5 feet or meters above that point. So we have our 19 kilonewtons per cubic meter times 1.5 meter. We see our total stress should be close to 199 kilonewtons per square meter. And then our pore water pressure, that's just how much water head is above our point. So at our point, the water table is right here. We only have 1.5 feet of water above our point. So this is 9.81 for the unit weight of water in SI. That up here. And then we multiply that by 1.5 meter. And that should be close to 14.7 kilonewtons per square meter. So our total effective vertical stress is equal to 99 minus 14.7, which is 84.3 kilonewtons per square meter. Okay, so this is something that we will write down and remember. But next, what we need is our increase in vertical stress. So remember that our increase in vertical stress is from the point load. It is a taken directly under and taken at top or on top of clay. That means Z is equal to 4 meters. So from this, you would reference lecture 3, I think, and then find the point load equation. You'll see that delta sigma Z for a point load is equal to that point load divided by Z squared times an influence factor I. And this influence factor I is a function of the radius and the depth. So the radius in this case, since it's directly under our point, is 0. And then Z is 4 meters. And all of these produce an I1 value of 0.4775. What you do is we then plug this here. So delta sigma Z is equal to the point load equal to the point load. So 1,000 kilonewtons divided by 4 squared and then times 0.4775. So 4. We do this out and we see that the delta sigma Z is 29.8 kilonewtons per square meter. That's what I was looking for. Okay, cool. Okay, so remember we have this equation. We found before that our vertical effective stress is equal to 84.3. That's kilonewtons per square meter. We found that our change or increase in vertical stress is 29.8. And that also is in kilonewtons per square meter. We're also told that our void ratio is at 0.78, and that is in no units. Our CC, our coefficient of compression index, is 0.216. And then we also know that our H is 3 meters. Now we can plug everything in. So we see that our SP is equal to our 0.216 times our height. Always note this unit of measurement here. It's also 1 plus 0.78. Don't forget the log. And we have 84.3 plus 29.8 divided by 84.3. What you'll see is all these units cancel out except for this one, the meters. So that would mean that our SP number is going to be 0.0485, and this is in meters because of that H value. So always double check this. A lot of times this H value is going to be given to you in feet or in meters because that's what geologically these levels of soil are that we're detecting. But oftentimes what you're going to need to report your settlement is in millimeters or inches or something like that. So always make sure to note that conversion. So generally what we would show this as, we would never tell the contractor or tell the client like, oh, you're going to get 0.04863,432 meters of settlement. And we'll just say something like, okay, this is about 50 millimeters of settlement is what you could expect here. If I got that right, 1, 2, 3. Yeah, 50 millimeters of settlement. And again, that's because all of this stuff is based off of assumptions. So this H of 3 meters, that's based off of subsurface testing. It may not be exactly 3 meters everywhere. This 0.216, that's from the slope of a curved line that is not a straight line. And we're just making that value count. Everything else we're assuming, there's just a lot of assumptions on there. So keep that in mind when you are looking at or presenting this information. We can't be too accurate. Okay, so that's it for normally consolidated. What I wanted to just quickly go over is the over consolidated looking into next week. So again, just to recap stuff, normally consolidated soil, that is when our current stress is the max stress. So therefore, current effective stress is equal to the past maximum, the pre-consolidation pressure. For over-consolidated, this is less. So our current is less than the past max. So therefore, our current is less than our sigma C. Remember what the curve looks like for our consolidation curve. We have a point. This is just kind of roughly estimated, but this is our sigma C. Then we have two kind of functions or two like lines that we say anticipate the behavior. So we have our CS or our CR, and then we have our CC. So if it's normally consolidated, we are always going to be greater than our delta C. So we're always going to be on the CC line, right? Like if we are starting at this point and we are adding a delta sigma Z here, then we're always going to be either traveling up this or backwards on our compression index. However, if we are over consolidated, that means we could have a current effective stress somewhere down here. It's for OC, right? And we're less than our previous pass max. So that would mean if we add delta sigma Z, we are on the CS line or the CRR line, or we could be on both lines. If we add enough stress, delta sigma Z, then we could go past our previous max and now be traveling on the CC line, right? So OC is a little bit more in depth when it comes to the calculation. So for the OC soils, what we'll see is the consolidation could potentially follow two paths. But it depends on the delta sigma z amount. If it's a little bit, then maybe it stays on it. But if it's a lot, then it could push it on over to the CC. It also depends, obviously, on the pass max compression and the current. So if you remember, that's where that OCR, the over consolidation ratio, helps, because it wraps both of those terms into one fraction of a term instead. So again, this is what we'll cover on Wednesday's class. Some updates for the week. Again, it's February, tomorrow. We are going to have your exam one sneaking up on you like sneaky fast here. February usually goes pretty quick, so keep an eye on that. And your homework one is going to be posted not on Thursday, dang it, on Wednesday. So just wanted to put that at least on your radar. After the class on Wednesday, homework one will be posted and you'll have a little over a week to complete that. Okay, thanks guys. Enjoy the rest of your evening and I'll see y'all on Wednesday.